So on the bottom of the purple polymer practice sheet, we have some problems where we have the polymer already, and we're thinking, if this is the polymer, how would we be making this polymer? And that's the same as on the other practice sheets as well. We have a top side where we have uh, the reactants, and we figure out the polymer, and then the bottom side is if we want to make this polymer, how would we make it? And the first thing that I would do is to get a better idea of what's going on here, to show another repeat unit or two, so we can see what is going on here with this. What does the polymer really look like? And the reason I do this is then you can look at the specific functional group that you have in the polymer and think about how I would make that functional group and see what's going on both sides. I mean, if you look at it here, then you can, of course, imagine this oxygen is bonded to the phenyl group, which is bonded to another CH2, but it's easier, I think, to draw it out. And the reason is, if I look at this ether and I say, how do I make ethers? Well, if they're symmetrical ethers, I would make them by dialcohols and sulfuric acid. It's not symmetrical. Different group on this side than that side. If it has one group on one side that is primary, then I can make it by Williamson ether synthesis. That would be my second choice. And this is primary, and this is aromatic, so clearly not primary. And so if this is primary, then you could say this part used to be have the leaving group on there. Okay? And same over here on this one. Primary used to have the leaving group on there. So if you draw out a bunch of them, and you can say, okay, now the starting material is going to have, on one side, it's going to have a CH2 and a leaving group, and then we have the benzene ring, and then on the other side, that is the alcohol in Williamson ether synthesis. And of course we have to deprotonate the alcohol, so our reaction then, it will be starting with this monomer, which won't do anything until we add sodium hydroxide to deprotonate it. Okay, so this is the method then of forming this polymer, coming up with a monomer with a nucleophile on one end and the electrophile on the other, and making sure that we have the leaving group on a primary carbon, so we get substitution and not elimination. Okay, let's look at the next one. I'm going to do the same thing here. We got the show out several units here, so 1, 2, 3, then it goes to an oxygen again. So it's 1, 2, 3 in the repeat chain. 1, 2, 3 to an oxygen again. 1, 2, 3 to an oxygen again. And then on every single one of these carbons, I have a methyl group. So methyl group going up there, down, up, down, up, down, up, etc. So this is what the polymer is going to look like. And again, I can pick something in the middle, say this ether, and say I'm going to make that ether. And again, go through the process thinking about what method that you might use. And in this case, we don't have, well, yeah, this is an interesting one. I didn't actually even think about this, but this is a symmetrical ether. And so we have, if you go to the left or go to the right, you see the same exact group. And when you're looking at it here, it's not quite so obvious until you draw the oxygen here. So what we do have is a symmetrical ether, so we could make that ether by, potentially we could make that ether by reacting the alcohol. 1, 2, 3 alcohol on the other end, and then adding sulfuric acid. And so this alcohol is going to react with the next alcohol in the neighboring molecule, and it could form a polymer there. So that is one way to make that one work. Could we make this by Williamson ether synthesis? Well, we have to look at the ether, look at either side of it. This side is secondary and this side is secondary. So neither side is primary, so Williamson ether synthesis will not work. We could possibly make it by alkoxymercuration demercuration, which would mean that you'd have an alcohol on one end of the molecule and then an alkene on the other end of the molecule. So if we did that, let's start here and go this direction. If this was the alcohol, then we'd have OH 1, 2, 3, and here's a methyl group here and a methyl group there. And so we have, if we're numbering this, 1, 2, 3, then this would be carbon 4, and there used to be a double bond between carbon 3 and carbon 4. So 1, 2, 3, and then there would have to be a double bond to carbon number 4. And so if we had this alcohol then would attack the next molecule on carbon number 3, and we could do it also by alkoxymercuration demercuration. So we already have the alkene dumped together with the alcohol because they're attached to the same molecule. Then we would just have to add our mercury trifluoroacetate in step number 1, and then step number 2, the sodium borohydride. Not sure that anybody makes polymers this way using alkoxymercuration demercuration. Actually, polymers are made by the cheapest way possible, usually requiring high temperatures and a lot of pressure, and so the sulfuric acid method would suit itself very well for that. But again, it's a thought exercise on how you might piece these together. So you can go ahead and work on the next ones here. Next one is a poly ether, and you see there's 2 ether groups there, and so there's 2 different kinds of monomers that are going to be involved there. And you see there's a benzene ring here, and then this is primary there and primary here. So you can imagine a dihalide there. And then the next one looks really ugly, but you should, especially if you draw this out, you should be able to reason out what you've been reasoning out in drawing products of epoxides. So what we see here is an alcohol, and then next to it on the beta carbon we see an ether. And so what you should start seeing then, imagining, and here is on the other end an alcohol next to beta carbon, which would be, if we're continuing on the parentheses here, then the next thing that it comes to is the oxygen here, and then the benzene ring, etc. But what you're seeing here then is that this is made by 2 different kinds. There's an ether linkage here and an ether linkage there, and then we have the 2 alcohols, so it's made by 2 different kinds of molecules. You could break it apart here and say this used to be the epoxide, and then on the other end that used to be the epoxide. See how that's coming together now? And so you have then a diphenol that you would deprotonate with appropriate reagents. So go ahead and work on 6 and 7 here, and there'll be an answer key for the purple sheet here, for the back side of the purple sheet, and then for the next sheet in your packet, which is the yellow sheet. So all of these are, you're making polymers, and or you're looking at polymers and showing the reactants. Okay, that's the end of our little unit on making polymers, and a couple chapters down the line we're going to be working with acid derivatives, and there's more polymers that we'll be looking at there, applying the concepts that you learned here. You'll be making some polyesters, some polyamides like nylon, etc.